Welcome back to the Chem OG. Today we're going to take a look at a very biologically relevant class of molecules known as acyl derivatives. And how do you identify acyl derivatives? Well, they're very obnoxious. That's not true. I'm just saying that to give you a way to remember these molecules by. Because acyl compounds are ones that contain a carbonyl carbon, and remember that's a carbon double bonded to an oxygen, and attached to that carbon is going to be either a nitrogen or an oxygen or a halogen. Now remember in organic chemistry we symbolize a halogen with an X, and so NOx, these guys are obnoxious. So to give you guys a couple of examples, we can take a look at an ester, and an ester is an example of an acyl derivative because it's an oxygen attached to a carbonyl carbon. We can take a look at an amide, which is a nitrogen attached to a carbonyl carbon, or we can take a look at an acid bromide, which is halogen attached to a carbonyl carbon. And so before we move any further, I wanted to review a couple of fundamentals with you. And so remember that in a favorable reaction, your reaction arrow is supposed to move away from unstable molecules and toward stable molecules. So to kind of show you visually how that looks like, we're going to move away from the unstable molecules and towards stable molecules. And so the setup that we have with nucleophilic acyl substitution is the following, is that we're going to have a nucleophile reacting with an electrophile, and attached to that electrophile is something that's going to act as a leaving group. It's going to take off. And so what we'll do is we'll form a new bond between the nucleophile and the electrophile, and in the process the leaving group is going to leave. And so here's our product. And our leaving group is going to be all alone and kind of by itself. And so what we want is, in order to make this reaction happen, we want this side of the reaction arrow to be unstable. So we want a really unstable nucleophile or a strong nucleophile. We want a really reactive electrophile. And we also want this leaving group to leave readily. And the reason for that is, when that leaving group does leave, we actually want it to be stable. So the general reaction is going to look like this. We're going to have a NOx attached to our carbonyl carbon, and the rest of this molecule is variable. We're going to have a NOx attached to our carbonyl carbon. Remember that carbonyl carbons are electrophilic, and so a nucleophile can come in and attack that carbonyl carbon, and that'll move these pi electrons here up to the oxygen. And when that happens, the pi bond is going to disappear. And that should remind you of a few of the reaction types that we spoke of before, and that is that this is a reaction that's known as an addition reaction. So whenever a pi bond disappears, this is an addition step. So when you have a molecule that contains a charge, or a portion of a molecule that contains a charge, that's not really a good thing. You want that charge to go away. So it's very possible for that negative charge to move away from that oxygen. And so here, as of this point, our nucleophile is bonded to our carbonyl carbon, or what used to be our carbonyl carbon. It's no longer that. And so here's the carbon. It's attached to an oxygen with negative charge. Here's our nucleophile. This is what we call a tetrahedral intermediate because there are 4 things attached to our carbon. Now, it's also called an intermediate because it's not going to last for very long. So that negative charge on the oxygen can move back down and reform that pi bond. Now, when it does, something has to give because carbon can't make 5 bonds. And so what's going to happen is that the NOx group is going to act as a leaving group. Okay, so that's the reason that these molecules are so special, is because they have a functional group attached to our carbonyl carbon that is, or that can function as a leaving group. And so when that NOx leaves, the pi bond is going to reappear and the NOx group is going to leave off on its own. And what we will have is we'll reinstate that pi bond, and now what's attached is our nucleophile. So that step in which we form the pi bond is an elimination step. So altogether what we did was we had a carbonyl, we restored the carbonyl, and so that's known as a substitution reaction, and that's why I'm referring to this reaction as an acyl substitution. Now, on some exams, like for example on the MCAT and on the DAT, this reaction is known as an addition-elimination reaction and not a substitution reaction. And usually that's to distinguish it from SN1 and SN2 reactions. And so this particular reaction is known as an addition-elimination reaction on some standardized exams. And in order to go through this elimination step, we had to have a NOx that we can kick off. So there's no way to go through this elimination step unless there's something here that can be kicked off as a leaving group. If instead of a NOx here, if instead of a nitrogen, oxygen, or a halogen, if we had a carbon or a hydrogen, that would not be a good leaving group, and we would not see that elimination step occur. So acyl compounds are also known as carboxylic acid derivatives. And again, depending on your exam, you may not see the word acyl at all. You may see carboxylic acid derivatives. And the reason these guys are called carboxylic acid derivatives is that we can derive them or make them from carboxylic acids. So what I wrote down here is the original sort of generic reaction that we had going on. And so the NOx adjacent to the carbonyl carbon, as we saw, is that potential leaving group. If that leaving group can be stable on its own, what that does is it means that the molecule's very likely to react. Okay, so if I can form a stable product here, that makes the reaction more likely to occur. Now, going through the mechanism and understanding the reactants and the products, that can be a very, very time-consuming process. So what you can do instead is the following. If we're trying to identify the leaving group, well, the leaving group is originally attached to our electrophile. And so by taking a look at immediately what's adjacent to our carbonyl carbon before any reaction occurs, can give us a good idea about how stable that molecule is. If what's attached to my carbonyl carbon is going to be a good leaving group on its own, then my original molecule is unstable. If it's a terrible leaving group and it won't form on its own, then that means that that leaving group is going to stay and it's going to stick around, and it makes the original molecule a little bit unreactive. So let's try applying that principle. So the first molecule we're going to take a look at is an acid bromide. So what I want to do is I want to take a look at what's immediately attached to my carbonyl carbon, and that is a bromine. And so this is an acid bromide. And if that bromine leaves, the bromide is a great leaving group, and that means that that acid bromide molecule is reactive. If I take a look at an ester instead, on an ester, that oxygen that's going to leave has an ethyl group attached to it. Okay, so on this ethyl acetate molecule, ethoxide is a strong base, and that makes it a poor leaving group. So that means that that leaving group isn't going to leave, which also means that that molecule is not going to detach. And so that makes the molecule rather stable. Esters feature biologically as stable functional groups. So some examples that or reaction examples that we might take a look at involve trying to determine which side of a reaction is the one that's more favored. And so remember, the reaction arrow is going to point towards the stable side. So on the left, I have an amide, and this functional group right here that could leave is a terrible leaving group, right? So that methyl amide is really unstable. It's got a negative charge on a nitrogen, and that's not all that stable. But if I take a look on the molecule on the right-hand side with this acid anhydride, the leaving group that could leave is an oxygen with a negative charge. But that oxygen with a negative charge doesn't have to keep its negative charge solely on this oxygen. It can move through resonance to the oxygen next door. And so because my leaving group is stabilized by resonance, that makes it more likely to leave. And remember, if this molecule is more likely to break apart, that means that it's more reactive. And we're going to point away from this molecule and towards this molecule instead. Okay, so our reaction favorability is very much going to favor the amide, and it's going to leave the acid anhydride alone, which means that that acid anhydride is actually quite reactive, and we're a lot more likely to make an amide. And so a word of caution here is that when you take a look at these types of reactions, your knee-jerk reaction might be nucleophile, electrophile, hook them up together. Okay, but there's one situation of which I want you to be aware, and that is whenever you have a carboxylic acid and an amine. So this nitrogen is nucleophilic and this carbon is electrophilic. But the reaction that happens is not going to be a nitrogen attacking this electrophile and making an amide. What's going to happen preferentially is this nitrogen is simply going to take away a proton from this acidic carboxylic acid, and we will form this salt over here. Okay, so that's the more likely reaction to happen. So always watch out for acid-base neutralization. Whenever you have a carboxylic acid and an amine, the neutralization of the proton is much quicker and it's more favorable than nucleophilic attack. So to summarize, here's what we talked about. If you have a molecule that has a pretty bad leaving group, well, the leaving group isn't going to leave, and so that makes the molecule more stable, right? Molecules that go through fewer changes are ones that are more stable. And if we're talking about what kind of leaving group is worse than others? Well, that NOx mnemonic that I gave you actually provides you with a ranking. So the molecule that's going to be the most stable is the one with the nitrogen attached. The molecule that's going to be the least stable is the one with a halogen attached. And the oxygen leaving group is somewhere in between, and it depends on whether or not it has resonance. And so these molecules go through an addition-elimination reaction, and that elimination step is only possible if there's a quote-unquote good leaving group. Thank you so much for watching this video. Please be sure to support this channel by subscribing, and if you've already subscribed, make sure to hit the like button as well. See you next time.